Hello everyone, welcome to my final presentation project of Introduction to Operating Systems class. During this presentation we will be exposing the vulnerabilities existing on the advanced metering infrastructure that have been implemented using IoT and its possible solution in terms of communication by utilizing end-to-end encryption. IoT is a cutting-edge technology which is being used for many purposes like smart homes, manufacturer industry, utility companies, etc. This is our roadmap. We will be first of all making an introduction about the topic. Then we will explain why we got the motivation for writing down this paper. Also, we will show the related research about the topic, and based on the hypothesis we will make some demonstrations, and we will conclude talking about the future work. Let's get started. The Internet of Things has become one of the most convenient technology in terms of smart devices communication. This includes wide-scale automation in industries like manufacturers, health, smart homes, artificial intelligence, etc. Many companies have jumped into this approach in order to automate their processes and data collections for optimizing their options and operations, also providing insights of the service to the users and themselves. Many utility companies across the United States and around the world have jumped into this amazing solution for power grid, including the water and gas services. This technology is really dependent on synchronous communications between the devices and the utility or energy provider. Also utilizes elements like smart meters, sensors, mesh networks, etc. In an implementation of this kind, there are some critical components like methane sensors, life support equipment, lower explosive level. These elements have very poor IoT security or have no data encryption at all. This information is encoded in concise binary object representation, or a CBOR, which is very easy to decode and is being used to send information over the network utilizing an MQTT broker, which is the messaging distribution system for all the consumers subscribed to it, and probably with no level of encryption. What if the system on the broker end is compromised, or the messages might get intercepted by any malicious hacker? Well, at this point of time, the communication is vulnerable and the data integrity and the confidentiality are in jeopardy, or can be changed on the fly that can cause any attack like a denial of service or causing any system malfunction. This is an overview of the current design of the AMI implementation. It comes with a firewall between the consumers, which represents the utility data entry. The information advertised is hashed by concise binary object representation with no encryption at rest. The MQTT broker is being managed by cloud service, which delivers all the messages sent by the methane sensors producer to the consumers on the data center. The electric utility sector's grid modernization efforts. The utility AMI platforms allow central communications with thousands of smart meters across the cities and outside of our homes and businesses through a field area network. The core value of the AMI investment is to allow utilities to drive efficiencies in meter readings, meter turn on and off activities, customers' interactions, and outage management responses. The innate advantage of the utility AMI platforms is that they usually have full market coverage across the customer's base. In a connected world, this means that the utility AMI network interacts with a wide number of third-party devices like sensors, controllers, and meters. As we explained previously in the current design, the messages payload travel with no level of encryption, which represents a huge vulnerability that could cause confidentiality or integrity issues. For that reason, we came up with the following hypothesis, which says as follows. Implementing asymmetric encryption on the message payload will enforce data integrity and confidentiality. As an addition to the current implementation design, we have included a SHA-256-bit encryption between the MQTT broker and the producer. The idea is to decrypt the messages at the consumer's end way before storing that information into the database. There's a level of encryption that will be handled by a public key and a private key. Every message sent by the producer is going to be decrypted at the end system by utilizing a private key. The redesign of this current methane sensors IoT implementation will contain the following critical elements: asymmetric encryption capabilities, SHA-256 encryption algorithm, and a public and private key pair. Let's see a demonstration about a possible solution for this problem. Let's see how the communication behaves between the producer and the MQTT broker by utilizing concise binary object representation. We will show how the data is being transmitted from the producer and how it's being received on the other side. If you see, the level of hashing of the concise binary object representation basically is equivalent to the same plain text that was sent by the producer. On the consumer's end, it looks just the same. In the following video, we will be simulating a possible solution for the existing issues in the current methane sensors IoT implementation. When we use end-to-end encryption, the behavior of the data transmission is totally different. Let's see how the data looks like when we use encryption, and we have to find this, for this example, a producer and consumer, which represents the end system in this case. Every one of those elements utilized a public key for the data encryption and a private key for the data decryption, for decrypting the messages. If you take a look now, the information is not human readable anymore. Otherwise, if we deactivate the encryption at the producer, the data will be shown at the same format that it was sent from the producer. So that's where we identify that the encryption is needed. So that's why we are using the end-to-end encryption, just to prevent that the messages could be intercepted and the data as well could be changed or stolen. After our previous demonstration, we might conclude that by redesigning this IoT implementation, we will enforce the data transmission between the methane sensors and the end system via MQTT broker, which at this moment is being only hashed by concise binary object representation. And only by implementing end-to-end encryption will guarantee a robust data integrity and confidentiality in the communications between the methane sensors and the end system. This solution could be implemented also in other IoT projects like smart homes, manufacturers automation, security surveillance systems, etc.